now maybe comment a bit more on this theorem we have derived just now. Let's look back to this equation here. What's our f? We have put together many things here. Yes, this. And so we can let me do it a bit more explicitly. Let's stay with this equation and put down what f complete is. Well, f is something like this. Yes. So we would have m alpha times well, let's stay with this t and v. What's t? T is this. And let's look at the special movement we have studied a little bit in detail last times. And that's the movement about the equilibrium. And look what those equations tell in this case. They are local. But the movement on the equilibrium is also local. So they can cover, well, the whole movement. Otherwise, we don't know. The movement can leave one parameterization, and you need another one to cover it. But in the case of small oscillations, you just stay within one parameterization, and that's something which we can discuss more in detail. So let just this alpha equal to 0 and x of 0 be equal to x0 be the point of equilibrium. What that means? Well, that means that the alpha is equal to 0 is a solution. So what's then let's P0 be equals to P of 0. So if I linearize this, linearize quadratic function means to put just let's see, this one, so we have m alpha, the kinetic energy, m of alpha, pt of alpha, p of alpha times alpha t That's what it is. See? This is a M times M matrix. This is M minus S times M minus S matrix. And now this is a number. So it's okay. So if I linearize this, I have to just, or to I don't know the best expression, quadratize it. I approximate is by the quadratic function. That this means to write down that's it. Or so this is now the kinetic energy. And what about the potential energy? Well, it is simply, it is this one. And if we linearize it, then we have, of course, we know that d of v of alpha, taking it alpha is equal to 0, is 0. So it is then approximated by, well, 1/2 should be here, by 1/2 alpha t d2 of v hat alpha, or well, alpha 0, alpha. So we get now a kinetic and potential energy of a harmonic oscillation, which is a known expression for us. And we know the solution. These are harmonic functions. It is an M minus S dimensional harmonic oscillator. Take this as the kinetic energy, this as the potential energy, and take these equations, you get equal to 0. So get again small oscillations are linear, even in the movement on a manifold. Just the same thing. Well, the question now arises, you will get some frequencies here, omega k, you know. And those will depend on this matrix and this matrix. They will be the eigenvalues of the matrix pair. But those matrices depend on the parameterization. You take another parameterization, you will get all the other matrices. So the question is, of course, those frequencies should not depend on it. If this is the same movement, but you have to prove it, of course. That I will leave you as an exercise. You will have to find a formula how two parameterizations of the same neighborhood on the manifold are connected. Well, you have a manifold, and there is your point of equilibrium. And that's the neighborhood where the movement is confined. And this neighborhood is obtained by two parameterizations. What's the connection? Well, connection is that those two regions which have the same dimension are connected by their diffeomorphism. It's a technical theorem which again depends on any time you are working with this, you are working with theorems on inverse functions and on the implicit functions, just the same thing. It is a technicality I will let, so that will be an exercise. I will write it down for you in a written form. Exercise, prove that the frequencies of a linearized system do not depend on the parameterization. This is again a technical, or better to say theoretical matter. Why? Well, because in computing, practically, such things, you will hardly take any parameterization. You will work directly. What that means? That means that you will have to linearize not the Lagrange equation, but the original equation where you see the manifolds. There. That much for local meaning of the Lagrange equations. But now, of course, you see, we would like to develop a theory, at least, as much general as we did with standard ODE systems. What we did there? We proved that we have something which was called maximal solution. And that's the only solution which is interesting in physics, the maximal solution. You will know where and when it begins and how long it takes and how it ends. The local solutions are well, just a technical tool. But now we have to cope with the fact that if you have movement, then it will not be covered by a single parameterization. You will always have to put down different parameterizations to meet your movement. And that's what we are going to do now. Should insert somewhere the correction of the proper error of the last time. And I'm just thinking, what would be the best place for it? Well, I think the best thing is to continue with this matter once we have begun with it. Okay. I will now state at least the theorem. Whether I will be able to prove it within this hour, I don't know, but I will state it. theorem. Let M be a smooth manifold defined by regular conditions such that M contains omega, contains X, goes into GA, GI of X equals 0, and B, a smooth, again, then for any x0 from M, there is a maximal solution of what? Well, not of Lagrange equations, because they are just local. But we have an equation which has a global character, and that's the equation of Lagrange of the first kind. Of satisfying x of 0 equals to x0 and x point of 0 equals v0, well, v0 is from the tangential space of x0. So what is given? Given are those two vectors. One of them is on the manifold, the other one is on the tangential space. These are reasonable initial data. And for them, you say there is exactly one maximal solution of this system. In which sense maximal? Well, maximal is that there is not any other solution which is larger than it. That's clear. Definition of a maximal solution is clear. And the uniqueness, again in the sense we used it before, any other solution of it is a restriction of it. Unique. Any other solution y should be contained in it. The proof is in fact mimicking the main theorem we have proved already, with some modifications due to the fact that we are on the manifold. The definition interval, it's still the part of the statement. Definition interval I of x is open. And the set. And set x of t, x dot of t from I x sets equal or less or equal to 0 respectively. These are two sets. Are contained in no compact subset of what? Well, of the big space in which everything is moving, and that is m times r, m times r. These are the positions, these are the velocities, and this is the time. If you compare this with the standard theory, you will see that it is completely analogous. Now, proof. I will just stress those points of the proof which are different from the standard ones. So, for x0 from m and v0 from t of x0. We take a parameterization around x0. What do me the theorem about parameterizations always say, take any x from the manifold and I will give you a parameterization covering a neighborhood of it. That's what it is. So we do it now. We have a parameterization P such that to this x0 and v0 there correspond unique alpha 0 such that p of alpha 0 is x0 and v0 is sum of beta I 0 dp d alpha I taken at alpha 0. V0 is a linear combination of the basis of the tangential space, which is given by the derivatives of the parameterization. That's our geometry, which we know. So now, as I said we can now write our system in the following form: m hat with -1, f alpha, alpha dot. All together, this is some, and this is smooth. So we have a standard theory which guarantees there is an open interval AB around alpha 0 and a unique function and a unique function t into alpha t solving this under the conditions alpha from 0 equals to alpha 0 and alpha dot from 0 equals to beta 0. These are the components. Now, this solution is unique locally on this small interval. That's the theory which is guaranteed. And the same way, we know that again on this interval, no two solutions can cross, then cannot separate. This is just the other way of stating uniqueness. So the same now is true for any two solutions of the general equation locally. So if you have same point x0 and you would have two solutions through it, then this would give you can use the same parameterization because you are in the neighborhood of the same point. Two different solutions in the standard case, impossible. Once you have this, you can now define your maximal solution and everything is just the same as in the general theory. Now, there is an interesting corollary. This is a simple now difference to the general theory. If the manifold M is compact, then what you can say then? Then the definition interval of x is equal to minus infinity plus infinity. On any compact manifold and any smooth force you can imagine, the movement takes the whole time, back and forwards. Why? Well, because of this. This stays compact, and now this must be not compact. That means it should go to infinity. There is another much more difficult, but still an interesting exercise. What is the movement on a manifold if Please correct that. That's a force. Because Now I would like just to put 0 here. The question is it, well, everything is correct what I write down, even with 0, but it's not general enough. So now we have just f equal to 0. And the question is, what's the movement there? Can you say anything more precisely, more precise about the movement? You have a manifold, you have a movement, no forces. Take a sphere, take a plane. You have a plane, and you have particles moving on the plane, no forces. What's the orbit?
It's going to keep going.
Straight line, of course. Okay. Take now the sphere, no forces. What's the orbit? Huh? The so-called main circle. Main circle. And what's the common property of the straight line and the main circle? Is there anything common to them? That's the lines of the shortest distance. Shortest distance. These are the geodesics. And that's the general theory. If you have a movement on a manifold with no forces, then the system moves on the geodesic curve. That's a very fine, nice theorem which shows that practically the whole mechanics is exhausted with the differential geometry. If you understand well the differential geometry, you will understand mechanics completely. And, well, one of the last mega theorems which were proved in the last time, the celebrated Poincaré hypothesis, was also a kind of such thing, that the character of the manifold was proved not by topology, although the question was topological, not by differential geometry even, but by difficult nonlinear partial differential equations. That's the, you know what the theorem is. What Poincaré hypothesis is? Well, take any curve in the plane. Now, it's a bit plausible that if you a bit stretch this thing, you can put it to a circle. Yeah. Move it continuously, nicely, then you get a circle. By moving, I mean you should not cross it yourself. So, for example, this one wouldn't be reducible to a circle. Well, what's the difference between those two curves? What would you say topologically? What about a surface in the plane, in the space? If it is compact, if it is closed, if it is simply connected, then it can also be stretched or, well, nicely deformed to a sphere. And then the critical question was, what about a three-manifold in R4? That was the difficult question. In higher dimensions, it was known for long ago. But just the point 4 was difficult. And why was it difficult? Because the 4 is the dimension of our space in which we are living. 3 dimensions for space and 1 for the time. And that's what Perelman proved. I think it's some 10 years ago, that any simply connected closed surface in our 3-dimensional surface in R4 is deformable into a sphere. And it took 18 man-years to check the proof. That means that 6 people were working 3 years to go to the proof. And Perelman did it completely alone. Nobody knew that he was working on it for 3 years. Absolutely alone. And by the way, he refused all prizes he was given for that. $1 million in America, Fields Medal, everything. Didn't publish it. He put it on archive. A bit not everyday behavior, but the theorem was correct. So I see that the sometimes simple. Here you see that analysis, but this finite dimension analysis governs the mechanics. But in fact, if you wish to go a bit further, then you will see that very fast some partial differential equations will emerge, even in classical mechanics. Even then, partial differential equations govern continua. Is it so? Classical mechanics govern finite system of points. And partial differential equations is like strings. This is continuum. But if you take a simple one particle movement in a potential, then for every initial condition you get a movement. For the other one you get another movement, and so on. Take all together, you get a continuum, which has some interesting properties, which are governed by partial differential equations of special kind. Okay, so I think now we could make a stop here, and then I will go to next time to repair, which I messed last time. Okay.